So I'm okay, right?
Yeah.
So good evening, Professor Bhattacharya. Can you hear me? Yeah, you have to unmute yourself.
Sorry, can you hear me now?
Yeah, yes, I can hear you now.
Should I keep my camera on?
Maybe until the talk begins. Once the talk begins, you can close the camera.
Okay.
Okay.
So this is an hour's talk.
Yeah, it's normally Colloquium goes for 1 hour.
Yes, please. Yes. Oh, thank you so much.
You're welcome.
Yeah. Should we wait for a minute and then we can begin? Yeah. So, okay, maybe we can begin. So, good evening, everyone. First of all, wish you all a very happy new year. And today, we have with us Professor Mishkatul Bhattacharya from Rochester Institute of Technology. So, we are very glad that you are here, Professor Bhattacharya. So, let me introduce to you Professor Bhattacharya. He has completed his PhD in 2005 from the University of Rochester. Then he has completed his first postdoc from 2005 to 2006 in Georgia Institute of Technology. Then he moved to his second postdoc from University of Arizona from 2006 to 2010. So then finally he went to University of Maryland, College Park for his third postdoc. And later in 2011, he joined Rochester Institute of Technology. And since then, he is working as a faculty member in Rochester Institute of Technology. And his area of research is, theoretical quantum optics. He is expertise in that, and we are very happy. And is also our year's first colloquium. So please continue. Yeah.
Thank you very much for your kind introduction. Can you hear me?
Yes, we can hear you.
Can you see my slides?
Yes.
Okay.
Yes.
Okay. Happy New Year to everybody also. I'm very pleased to be here, and actually I'm happy I could come physically to your beautiful campus where I have been before, so I know exactly how beautiful it is. And I hope everybody is safe during these times. So yes, I would have liked to give the talk in person, but to be safe, we have to do things online. So I will now I should thank Professor Tarak Nath and Professor Ramurendra Sharma for inviting me and allowing me to share some of the recent results from my group. So, as was mentioned, my interests are in theoretical quantum optics, and today I will be speaking on cavity optomechanical sensing and manipulation of an atomic persistent current. These are the pictures of my collaborators. So Pradeep and Tushar were the two postdocs who did most of the work. Christian Feliz was an undergraduate physics major. Professor Kanamoto is a many-body theorist at Meiji University in Tokyo. Professor Anand Kumar Jha, whom some of you might know, is at IIT Kanpur. And this is Professor Mingshen Chang from the Academia Sinica in Taiwan. So this is our recent work published in Physical Review Letters 2 or 3 months ago, I think in September. So here is a brief outline of the talk. I will introduce, this work combines two different subjects, so it's a little bit unusual to have to introduce two different areas, but I will try to do it. And then I will describe our scheme for an important rotation sensing problem and some variations, and then I will conclude. So my talk will be about atomic Bose-Einstein condensates, and this was something predicted by Satyam Bose and Albert Einstein in the 1920s. And for the purpose of our talk, we can understand Bose-Einstein condensation simply as the manifestation of the wave nature of particles. So on the left, we have a schematic of the particles of a gas at around room temperature, where they behave mostly like classical particles, colliding with the walls of the room and with each other. And then as the temperature is lowered, their wave nature becomes more apparent. So these little waves are supposed to be carried around by each atom. And then when the wavelength becomes comparable to the spacing between the atoms, that is when critical temperature is said to prevail. And ideally at zero temperature, the entire sample of gas consists of one large matter wave where the wavelength associated with each atom is so large that they all become indistinguishable. So these were experimentally realized in 1995 and eventually recognized in 2001 with the awarding of Nobel Prize in Physics to Carl Wyman, Eric Cornell, and Wolfgang Ketterle. And here is an image of a typical Bose-Einstein condensate, usually confined in a magnetic trap. And the peak basically corresponds to this matter wave that I just described. The critical temperature can be written in terms of some constants, some fundamental constants, and scales as 2/3 of the density of the gas. And there is actually, since we are not at zero temperature, there is a thermal fraction. Only part of the sample is Bose-Einstein condensate. And the condensed fraction is given in terms of deviations from this critical temperature and goes as the cube of the deviation. Now, this picture I gave you was for non-interacting particles, but in these samples, the particles are weakly interacting. And as in any system of interacting particles, there can be collective excitations. We can think of them simply as phonons. And the energy epsilon of these phonons as a function of their momentum is given by this dispersion, often called Bogoliubov dispersion, after the scientist who first worked out the theory of weakly interacting Bose gases. And for low momenta, it scales linearly with momentum. And so it's said to be phonon-like. And for high momenta, it scales quadratically with momentum because the second term dominates here. So that's like a free particle. So the excitations are supposed to be particle-like. And the relevant scale is the velocity of sound in this gas sample that's given in terms of the atomic density, mass, and the chemical potential. One of the remarkable features of a Bose-Einstein condensate is its response to rotation. And in the earliest experiments, Bose-Einstein condensates, because they were made of gases which had atoms with magnetic moments, they could be confined in free space in magnetic traps. And then these condensates could be rotated using a focused optical beam. And basically, the interaction responsible for the rotation is light matter interaction between the laser beam and the atoms. And if the frequency of the light is appropriately chosen, stirring basically pushes the atoms in front of the stirrer. And in that way, angular momentum can be imparted to the cloud. Now, in acquiring angular momentum from the stirrer, the condensate behaves like a superfluid, not like a rigid body. So the only way a superfluid can take on angular momentum is through vortex formation. And here we see for light stirring a single quantum vortex of charge h bar. By charge, I mean angular momentum, which is actually precessing around the center of the condensate. And that precession is due to what is called the Magnus effect. This is something we see in tennis or cricket when a spinning ball has a different trajectory from a non-spinning ball. And this is often used by players to swing the ball or to hit topspin in tennis. And here the Magnus force acts perpendicular to the direction of the motion, so that results in actually rotation of the vortex around the condensate center. So these are images taken by sending light nearly on resonance with the atoms through the sample, and the dark area is the core of the vortex, which is being avoided by the atoms because of their rotation, and the movement of that core tells us both the charge, the sign, and the magnitude of the charge of this vortex. If we stir the condensate a little bit more energetically, we can produce vortices with higher charge. So you see a charge 2 vortex here, but if we stop stirring, then this single charge 2 vortex decays into 2 singly charged vortices. And this is simply because this configuration with 2 vortices is more energetically feasible than has lower energy than the single charge 2 vortex. Okay, so the higher charge vortices are not stable, they decay to lower charge vortices. If we stir even harder, lots of vortices appear. They actually repel each other and they arrange themselves into a triangular lattice. These have been predicted and seen for superconductors also. So these are, I think, were predicted by Abrikosov. And these are observed in 2001 at MIT for Bose-Einstein gases. So there are lots of interesting rotational phenomena that can be seen in these condensates. But remember that I said these condensates were basically confined in a harmonic trap, and we can talk about these traps as being simply connected, which means the distance, the path between any 2 points in the condensates, the shortest path between any 2 points in the condensate goes through the condensate itself, right? To reach from one part of the condensate to the other, you just take a straight line and it goes through the condensate. A little bit later, experimentalists began to place Bose-Einstein condensates in multiply connected traps. So here, for example, is an annular or toroidal trap. And here you can see that the path required to go from one point in the condensate to the other is not always a straight line. So for 2 diametrically opposite points, you have to go around in order to reach the other point. And so we call these multiply connected condensates. And what's interesting about these is that forcing the atomic density to 0 at the center of this ring stabilizes the rotation. It offers, in more sophisticated terms, a topological protection. And you can see that in this panel here, where you have 2 sets of data. This one, which is the probability of survival of charge 1 vortex, you can see the vortex disappears very quickly, happens when you just have a harmonic trap with nothing in the middle. If you ignore this peak in the middle, just a harmonic trap, you set the condensate into rotation. And here is the survival probability if you have a light beam going through the center, which repels, just like the stirrer, the atoms from the center. So the atoms are forced to occupy a ring, and now the rotation can last for a much longer time. In fact, nowadays it's quite easy to have these persistent currents with charge 10 or 12, which rotate for minutes, which is a very, very long time for a quantum system to show coherence. So we can simply think of this entire object as being constituted by waves, and write a simple wave function, often also called an order parameter, for any rotational state created on this ring. And the amplitude of this rotational state is given by the square root of the atomic density. And the phase is given by an imaginary exponential, where L is an integer that basically corresponds to the angular momentum per atom in this ring. So for L equal to 0, there is no rotation. For L equal to +1, there is rotation clockwise, if you assume that convention. And for -1, there is rotation in the other direction with 1 h bar per atom in the ring. And if you plot the energy versus angular momentum per atom, then you see it's a periodic quantity, and the minima of these energy correspond to these rotational eigenstates, these persistent current states. So these are not infinitely stable, but they're metastable. They last for a long time. And as you can guess, you can switch from one state to another, basically using two mechanisms. One is climbing over this potential hill, and the other is tunneling through the potential barrier. So these changes in state are called phase slips. I will explain why in a moment. But the mechanism which allows you to climb over is called a thermal phase slip, and the mechanism which allows you to tunnel through is called a quantum phase slip. And if you plot this wave function, say for charge 5 versus a charge 4, basically you have a wave going around in the ring, and if you compare the two, you will see that charge 4 rotation has 2 pi phase less than charge 5. So if we slip from 5 to 4 bar per atom, we basically lose 2 pi phase, and that's why it's called a phase slip. Now, lately, these systems have become very, very popular, and people are using them to explore superfluid behavior in a very controllable way. The experiments allow the scientists to have a lot of control over the geometry of the trap, the transport of the atoms, and because the atoms have internal degrees of freedom, they can also be exploited for manipulating the system. And so, of course, it's a very good platform for studying wave phenomena associated with superfluid hydrodynamics, so shock waves, hysteresis, and so on. This is a good geometry for doing atom interferometry. You can build the prototypes of analogs of electronic circuits, which are called atomtronic circuits. So in electronic circuits, electrons carry the current and they are charged. And here atoms carry the current and they are neutral. And you can put say a barrier on the ring, a small barrier on the ring, which then serves as something like a Josephson junction, familiar from condensed matter physics, and also design other things like diodes and transistors. So that's an active area of research using these ring condensates. More fundamental studies have been proposed for realization of time crystals, and as I mentioned, studies of topological defects, and even simulating the early universe. So I told you that the rotation could be generated by stirring, just like you stir your coffee with a spoon. There are actually there are several ways of creating rotation. So like I said, the atoms have internal degrees of freedom, and those can be exploited using two photon transitions called Raman transfer schemes to set the condensate into motion. You can also set the condensate into motion stochastically. Meaning you will create a current, but you cannot predict what the size or the sign of rotation will be. So this is an interesting system where you have on a ring a number of condensates created independently. So they have phases which are not necessarily the same as that of the neighbors. And then suddenly the barriers are all removed. So there is a phase gradient between any two consecutive parts, and that sets often the ring into rotation. And actually, this is exactly the famous Keeble-Zurek mechanism of creation of topological defects. And this has been verified experimentally. There are other ways of creating the rotation, but I won't go into them. I will talk about how to measure the rotation. So as you can imagine, with all these applications, it's very important to be able to measure how the superfluid is rotating. So the earliest methods basically required releasing the condensate from its trap and then trying to image optically the features of the vortex. And the reason you have to do that is because as long as the condensate is trapped, the core of the vortex is usually much smaller than the optical wavelength. So light cannot resolve that feature. You have to let the atoms expand ballistically, and then you can image these features in the density. So here is an image with no vortex. So upon expansion, the condensate appears to be more or less uniform. Here is expansion of a charge 1 vortex. And here is expansion of a charge 2 vortex. You can see the core of the charge 2 is deeper and bigger than the charge 1 vortex. And you can distinguish between simple holes in the density versus rotational features, because when you allow the gas to expand ballistically, simple holes will fill in because the atoms will rush in from all sides. But for a vortex, because of the circulation, atoms are kept away from the core, so they survive the ballistic expansion. A more sophisticated method of measuring condensate rotation is to interfere the ring with a disk inside which is not rotating. So if the ring is also not rotating and the disk is also not rotating, and you expand both of them and allow them to interfere, you will see, as shown in this panel, a series of concentric circles. However, if the ring is rotating, in one direction, and the disk is not rotating, then you will see a spiral with a certain handedness. And if the ring is rotating in the opposite direction, you will see another spiral, but with the opposite handedness. So using these pictures, you can tell the rotation of this ring. There are more complicated schemes which use internal methods, internal degrees of freedom of these atoms, and you can actually get a picture with nice lobes, with the number of lobes proportional to the charge of rotation. What I want to emphasize is that all these methods of measuring the rotation are destructive, meaning once you have taken this photograph, meaning the atoms in the condensates have absorbed the light that you're shining on them, they are no longer, they don't form a condensate, because the recoil from absorbing the photons and then re-emitting them destroys their motional coherence. They are no longer in sync with each other. They no longer act as a single atomic wave. So these experiments, they have to start with a fresh condensate every time the images are taken. So to summarize what I've said so far, measuring the rotation of a ring condensate is an important subject, because we would like to examine in real time what the dynamics of these systems are and the various excitations created in them. But the current measurement techniques are all destructive. None of them work without expansion, and they cannot be carried out in real time, because once you've made a measurement, then there is no option but to start with another sample. So our aim is to supply a solution to this problem. And to do that, we bring in a measuring tool, a sensing platform from a rather different area of physics. And this platform is called cavity optomechanics. And now I will explain that part of the work. So probably the most famous application of cavity optomechanics was the observation of gravitational waves, which was reported in 2016, and then the year after that was followed up with the Nobel Prize awarded to Rainer Weiss, Barry Barish, and Kip Thorne, who were the major figures behind the eventual observation of gravitational waves. And you can see why the device, usually abbreviated as LIGO, or Laser Interferometer Gravitational Waves Observatory, is a cavity optomechanical device. You have mirrors here which are facing each other, so they form cavities, and laser light goes in and bounces back and forth between these two mirrors and eventually re-emerges and is recombined on some optical device that sends a signal to a photodiode. And usually, so this arrangement, as I'm sure you know from courses on special relativity, is called a Michelson interferometer. And usually Michelson interferometer, you try to stabilize the position of the mirrors so they don't move. But in LIGO, actually the mirrors are hanging as pendula, as oscillators from supports, so that when the gravitational wave passes by, it affects the arms differently, and the path length between these two changes, and that results in a modulation of the light intensity registered by this detector here. In fact, you can see such a signal here, which is a chirp of a gravitational wave passing by. This is simply the photodiode intensity as a function of time, and this is what is supposed to happen according to the equations of general relativity when two black holes circle around each other and eventually merge, releasing energy, some of it in the form of gravitational waves. So what is remarkable to me about this, well, there are a lot of remarkable things. This instrument is extremely complicated and large. Each arm is a few kilometers long and so on and so forth. Everything is under vacuum. It's a tremendous piece of technical achievement. But let's just pick one number, which shows that the relative displacement between the two arms can be measured to about 10 to the minus 18 meters in about a second by this device. That's an extremely small number. That's 1,000th of the radius of a proton. And so what this is telling us is that this kind of an arrangement where we are trying to detect the mechanical motion of an object optically is a very powerful paradigm. In fact, there are now many groups across many fields of physics who are exploiting this paradigm, not necessarily on the kilometer scale, but even on desktop realizations in small laboratories for building devices that can measure acceleration or electric or magnetic fields or temperature or velocity. Anything that you can couple to the mechanical piece, you can measure with sensitivity using this interferometric approach and an optical laser. So there are many variations of this method depending on which part of physics you work in. You could be a cosmologist looking for dark matter. You could be a gravitational wave astronomer looking for black hole collisions. You could be a microfluidics person looking for transport of a certain fluid. You could be a biologist trying to detect small biological molecules, and so on and so forth. There are many geometries and types of oscillators and electromagnetic excitations that the optomechanics can host, and I'm showing a few here. So this is what is known in optics as a Fabry-Perot system. You have two mirrors, one of them can move, and this is the simplest realization. But you can also build a toroidal geometry where the mechanical motion is in the radial breathing mode, and the optics occupies what's called a whispering gallery mode as the light circulates around the circumference of this object. Here you have a half-transmissive membrane in the middle of a cavity where the other two mirrors are securely bolted down. Here is a nanofabricated zipper waveguide where acoustic and optical excitations can coexist in a certain part of this periodic structure, and so on and so forth. One of the realizations that followed is known as levitated optomechanics, and that basically means that the mechanical oscillator is no longer hanging from a support or tethered to a substrate. It's actually clamped optically, and this is known as an optical tweezer, and it's a very simple realization, but not a simple idea, that a focused light beam can trap a nanoparticle at its focus. And this is something for which the Nobel Prize was awarded in 2018 to Arthur Ashkin. And the motion of this oscillator can be detected by looking at the transmission of the cavity. And typically what you see is the transmission at the cavity and then some side bands due to the modulation at typical oscillation frequencies of this particle. And so that's the idea we'll use as we combine cavity optomechanics with our superfluid problem. I do want to briefly say that a formal mathematical description of the system in second quantized language basically involves the coupling of the photon number inside the cavity with the displacement of the mechanical oscillator, right? So this photon number is nothing but a constant times the intensity of the light inside the cavity, and the intensity basically represents the radiation force that the mechanical oscillator feels, and so force times distance is work, and this has the right units for being included in the Hamiltonian. So this is just the free mechanical energy. This is the optomechanical coupling term, and then this is the drive due to the laser from the external cavity. And this term with the tilde is just the free field energy. Okay. So we would like to use this very sensitive cavity optomechanical paradigm to measure our superfluid rotation. And so we are then faced with two questions. A, how are we going to couple the superfluid rotation to the optical cavity? B, how do we translate our rotation into this paradigm where the optical cavity can sense a mechanical oscillation? How do we translate the rotation into oscillation? So the first question is answered, how do we couple? By using light beams of a special kind. These beams are also a separate field of study which has become very popular since the early 90s. Basically beams that carry orbital angular momentum, and one example are Laguerre-Gauss beams, and we can see some of the intensity, the transverse intensity patterns for these beams here. In particular, we have this pattern, which is represented by 4 lobes of high intensity separated by these nodal lines, and these are the 4 lobes that are formed inside the cavity if you inject a superposition of these Laguerre-Gauss modes, and this is a superposition which involves plus 2h bar superposed with minus 2h bar. And these beams basically carry this angular momentum information in their phase profile. And so if you go around a charge 1 beam, you will pick up 2 pi. If you go around a charge 2 beam, you will pick up 4 pi, and so on and so forth. How do we map into the optomechanical paradigm of optically detecting mechanical vibration? I will describe that now. So we start with this ring BEC, and we assume that it is magnetically trapped, as it is in many experiments, and that it is already rotating. As I told you, there are many ways of making it rotate, so we won't go into the details of which mechanism exactly was used, but there are many ways. So it has angular momentum per atom h bar times LP, or ring number LP. Now we put these beams, these optical beams carrying orbital angular momentum plus minus h bar, and they are tuned in frequency far away from any atomic transitions, so that the atoms of the condensate don't absorb any of the photons and basically have their coherent motion destroyed. And as I explained, 4 maxima will be formed by the optical beam patterns, and that basically acts as a periodic lattice along the ring. With the right detuning again, you can choose this lattice to be attracting the atoms towards the peaks or repelling them. But in this case, it doesn't matter, because the lattice is actually much weaker than the potential energy of the lattice is much weaker than the energy of rotation. So actually the condensate rotation is not changed from LP, except in a very specific way, which I will now discuss. So remember, this is a matter wave that's going around in this circle. And this intense modulation acts as a periodic potential for the atoms. When you have a wave that meets a periodic structure, diffraction occurs. Usually, we have electromagnetic radiation coming out from a device like a laser, which meets a material grating made out of matter, and then the laser diffracts into various orders. What I'm describing here is the dual of that. Here we have waves made from matter impinging on a periodic electromagnetic structure, but the result is the same. We get matter wave diffraction. And so there's a zeroth order, there's a first order, there's a second order, and so on and so forth. In fact, you get diffraction from the originally circulating condensate into side modes, which are separated by 2L. This is simply because of the interference between the plus and the minus L beams. Okay. Now, if the lattice is weak, if this periodic potential is weak, then only first order diffraction matters. So we are going to start from this persistent current and diffract a small number of atoms, about 5%, into another persistent current at slightly lower angular momentum and another persistent current at slightly higher angular momentum. This diffraction process is, of course, reversible. These atoms which were diffracted out into the two orders also come back. Actually, they oscillate back and forth between these two orders, and that is our mechanical oscillator. Okay, so these are the oscillations that will be picked up by the optical cavity. You can also think about the whole ring now being in a superposition of LP minus 2L and LP plus 2L, and these will interfere with each other and they will modulate the density of the condensate, and then the light passing through will pick up these modulations. Basically, this is no more complicated than adding some side bands to the frequency content of the light beam as you modulate something in its path. In this case, it's this persistent current. So we claim that the transmission of this cavity should contain some signature of this rotational motion, because these frequencies, as I will describe, depend on LP. So here is the mathematical model. I don't want to say too much about it, except that it contains an integration because it's a many-body Hamiltonian. We are summing over all the atoms contained in the condensate, but because the atoms occupy the ring in a continuum, we don't sum, we take an integration. This is the term that corresponds to the rotation of the atoms. This is the term that corresponds to the interactions between the optical lattice and the condensate atoms. This is the cavity energy and this is the driving field. And in consistency with the physical picture that I gave you before, our matter wave now consists of the original persistent current and then two side modes at LP plus 2L and LP minus 2L. Okay, these are all plane waves and they're multiplied by their quantum operators. So it's still a quantum mechanical wave. And normalization of the wave function basically means that the number of atoms contained in the main persistent current and these two side modes all have to add up to the number n. There is some constraint on n if you want to treat this problem one-dimensionally, as we have written here, but I don't want to go too much into that. Once you plug in this wave function into this Hamiltonian, you get something very much like the optomechanical Hamiltonian I showed you before, in that we have the photon number in the cavity coupling to the displacement of a mechanical oscillator, except there is not one but two oscillators. There are the two side modes, basically labeled as C and D, and the frequencies of these side modes are given by a quantity that contains a signature of the persistent current motion. So if we write the equations of motion, we can make a very simple argument which tells us that we should see the motion of the condensate in the cavity output. And the simple argument is this. Imagine that damping and noise are negligible, which turns out to be true almost in this case. Imagine that the number of photons in the cavity is very small. So this term is negligible. Then you just have two harmonic oscillators oscillating at frequency omega C and omega D. And if the XC and XD are oscillating at those frequencies, and you plug that dependence in here, you can see that the field will also carry signatures of frequencies. So what we're saying very simply is that if you calculate the transmission of the cavity, they should have a couple of peaks at the side mode frequencies that I showed you here. From each of those peaks, you can get information about the original persistent current, the winding number LP, but it turns out a particularly nice combination is to look at the difference of those two peaks, and that is just linearly proportional to the winding number. You know everything else in this because the orbital angular momentum of the beams is known, the moment of inertia of the atoms going around the ring is known, and LP can be recovered from this expression. Actually, we have done some follow-up work with Professor Amarendra Sharma and his student Sanpreet. It's very nice work. We are finishing up, which will give us more information about this system. So these are some typical parameters. We consider sodium atoms, which are quite popular in these ring condensates. The radius is about 10 microns. The number of atoms is about 10 to the 4, 10 to the 5. The winding numbers that are produced, like I showed you, range from 1 to 10. I think the orbital angular momentum of light used is about 10. People can make very high, hundreds of thousands or tens of thousands nowadays. And the condensates are cold to about 10 nanokelvin. Those are also typical temperatures, very easily produced in the lab nowadays. So I will skip. Okay, I will talk about this. So we first start by looking at the equations of motion and the steady state. So basically we set all time derivatives equal to 0 and we see how the steady state values go. And if you look at the photon number inside the cavity, as you increase the external power, you see that for low powers it is monostable, but at high powers you get multi-valued solutions, and these are typical bistability curves for optomechanical systems. What's remarkable about this case is that you are seeing bistability at about 10 or 15 photons inside the cavity. Typically, bistability is considered to be a nonlinear effect where you need very intense light to create this kind of nonlinearity. But here, because the coupling between the light and the atoms is very strong, you can get effects already at tens of photon numbers. In fact, in experiments which are related to this, people have seen bistability at a tenth of an atom, of a photon, excuse me, on average inside the cavity. So extremely low photon number bistability. Going beyond the steady state, we look at the linear response, which means we expand around the steady state by adding a fluctuation to every quantity, the fields, the side mode displacements, and so on. And from these fluctuation equations, we can examine the transmission of the cavity, basically the noise spectrum of this phase quadrature. And as we suspect, we can see these two side mode peaks, and the solid lines correspond to the calculation done without taking into effect the collisions between atoms, and then the dashed lines correspond to the calculation carried out using taking those collisions into consideration, which is more realistic. But in each case, it turns out the difference between the peaks does not change appreciably, so you can still recover the condensate rotation. This is a plot which shows that as you increase in power, your noise decreases, basically because you are using more power to get better signal to noise ratio over your short noise or the fluctuations in your laser. But after a point, the noise again increases because now the effect of measuring the condensate begins to perturb the condensate itself, and this back action becomes important and increases with more power. So there is some optimum power often called the standard quantum limit, which is appropriate for carrying out this measurement. So we will basically do all our rotation measurements in that regime. We looked at the stability of the system to make sure we are always operating in this blue region, which is the stability regime. There is also consideration of how long this linear response holds that I used to calculate the spectrum. And so if you look at the top panel, you'll see that the peak any one peak of the two side modes retains its height very nicely if you increase the driving power to the cavity up to a certain point, about 30 femtowatts, after which the peak diminishes in height, so the signal to noise becomes worse and the measurement is no longer faithful. So we are actually very much to the left extreme of this region, so we are safely in the linear response regime and we can get an accurate measurement of the condensate rotation. And this calculation is without collisions and this is with collisions, and we still have a reasonable window in which to carry out our measurement. So we can actually calculate the sensitivity of the measurement given the spectrum, and I only want to point out to you that it's about 10 to the minus 3 hertz per root hertz. This is measurement of angular velocity, and this is actually about 3 orders of magnitude better, than any existing method. So our method promises to have a very good sensitivity. One thing I want to mention is that the measurement time, which can be calculated from our theory, is smaller than the time it takes for a single atom to complete an orbital period around the ring. It's very much smaller than the time of duration of a persistent current, which is minutes, and also much shorter than the time it takes for the atoms to eventually absorb a photon from the laser, which is still far detuned, but nonetheless, over time, the probability that you get some scattering event is not zero, but that's also tens of minutes. So this is a method that preserves the coherence of the condensate. We can also, instead of just using the optical radiation and the cavity as a passive means of measuring what's going on inside, we can actively engineer the system. And one example of that is how the light for different setting from the rotation measurement protocol can be used to entangle the two persistent currents. And so here we see a measure of that entanglement, which shows up after a certain amount of orbital angular momentum used in the optical beams, and disappears if the temperature is too high, because decoherence then destroys the entanglement. So maybe I can conclude here to leave some time for questions by summarizing. So we have proposed new optomechanical system, ring BEC in a cavity. So ring BECs already exist in many laboratories across the world. Cavities in the optomechanical sense are being used also in a large number of laboratories, but this is sort of the first time the two have been brought together to realize rotation measurement system, and we have shown that it can carry out this rotation nicely and also create entanglement. And then there is a lot of future work to be done, but I'll stop now and take any questions if there are any. Thank you.
Okay, thank you, Professor Bhattacharya, for a detailed presentation. So we have some time. We are well ahead. We are well in time, so we can have a couple of questions from the students as well as faculty members. The floor is open for questions, please.
Mishkat, it's Amarendra. Can you hear?
Yes.
Yeah, I have a very small question. I was wondering about the quality factor. Have you calculated what was the quality factor of the system?
Yes, so actually it is contained in the supplementary information of our paper. It's about 10 to the 6.
Okay, okay. Another thing, this whole thing cannot be taken into the unresolved, this what is called, regime, right?
So actually we are in the unresolved sideband regime. This is the bad cavity regime, which is actually good for measurement.
Okay, so therefore the quality factor has to be very low. It is around maybe 10 to the power 3, 4 or something like that. Maybe, right?
What is low quality factor and what is high depends on what the mechanical frequencies are.
Right.
So generally in optomechanics, people talk about hundreds of kilohertz or megahertz or at least a kilohertz type of oscillator. But we are barely at a kilohertz. So our mechanical frequencies are quite low. And so the cavity quality factor need not be that low.
Okay. And this bipartite entanglement thing, can you elaborate a little bit more on it? This is.
Yes. So this is basically entanglement between the side modes, which are rotating with angular momentum LP minus and plus 2L, and they are interacting with each other through the light field inside the cavity. That is what is causing the entanglement. And assuming that they are in the approximation that they are both in some sort of or light and both the side modes are in Gaussian states, we can calculate the entanglement from the covariance matrix that comes out from the linearization process that I described to you.
Right, right. Okay, thank you.
Okay, so next Professor Tarak Nathe.
Mishkat, can you hear me?
Yes, yes, sir.
Yeah, you have included the noise, right?
Yes.
Was your calculation sensitive to the noise, be different kind of noise, or it will
So,
give the same result?
right. Our model includes only white noise. So the noise sources have zero mean and they are delta correlated in time.
Mm-hmm.
And the only place where we have varied the noise, actually, you can see the slide here. So as you change the temperature, of course, the intensity of the noise changes. But we have not looked at colored noise or any other kind of frequency dependence, if that's what you mean to ask.
Yeah, yeah. Okay. Thank you.
Thank you.
Yeah.
Questions from students, please. Yes, Samit.
No, sir, can you hear me?
Yes, sir, I can.
Yeah, actually, I did not clearly understand. So, which information actually we can find out from that basically that transmission basically. So, what is the information we are gathering from here?
Very good question. So we have, let me go back to even further. We have a Bose-Einstein condensate trapped on a ring, and it is
Yes.
rotating.
Mm-hmm.
And we want to know how fast it's rotating.
Okay. Okay.
That angular momentum is what we are trying to detect.
Okay. So that rotation angular momentum of the that BEC, right?
Yes, exactly.
Okay. And without any destruction of that BEC.
So I will be a little bit careful when I choose my words. I would not say there is any destruction. There is minimal destruction. So we are taking out about 5% of the atoms from the condensate, but the remaining 95%, nothing happens to them.
Okay, so that 5% basically going to the sideband regime, right?
Yes, yes.
Okay, 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 sir.
Exactly.
Thank you, sir.
Thank you.
Samit, if you are done, you can lower your hand. Okay, more questions. So, Professor Bhattacharya, so you are here for some time, tomorrow or day after tomorrow?
Actually, I'm leaving tomorrow morning.
Tomorrow morning. Okay, fine. Okay. Sanket Das. Yeah, Sanket, unmute yourself and then speak.
Hello.
Yes, Sanket, I can hear you.
Yeah, sir. Sir, actually, I didn't understand how the sideband is generated. Can you please elaborate once again?
Sure. So the sideband is generated by a diffraction process, which is shown here. So I am assuming you're familiar with normal diffraction, where maybe a beam comes out from a laser and you have a grating in its path. And because the grating is periodic, and there are transmissions both into the undiffracted as well as the diffracted orders of the laser. And if you look at the intensity of the light on the screen, you will see that for higher orders, it is lower. So the process that is happening to generate the side modes in a BEC is very similar, but the roles of light and matter are exchanged. So instead of a light beam which is coming to a periodic structure made from matter, we have a matter wave which is incident on a periodic structure made using light. So initially, there was only a matter wave with angular momentum h bar LP, but after diffraction, we have more waves added with angular momentum h bar LP plus 2L and h bar LP minus 2L. Of course, there are also higher order diffraction processes. So you will have h bar LP plus 4L, 6L, and so on. But those we assume are negligible. They are not very large, and not many atoms pick up that kind of angular momentum because the periodic structure is very weak. Or the potential energy of the periodic structure is much lower than the rotational energy of the condensate. So that is the mechanism by which these sidebands are created.
So, sir, if we increase the potential energy of this barrier, then how this result will be changed or?
So if we increase the potential barrier of the optical structure a little bit, we should take into account higher order diffraction. But if we increase it beyond the rotational energy of the condensate, then the atoms will stop rotating. They will become trapped between the maxima of the potential, right? Because the atoms will not be able to climb out of these wells.
Mm-hmm. Okay, sir. Thank you.
Okay. Any further questions or comments? Okay, I see none. So in that case, maybe let us thank Professor Bhattacharya for nice talk. And also, it's unfortunate that we could not have an offline presentation, though you are physically present. I mean, hope you will visit again so that we can have a offline presentation once again in future.
Thank you for asking. It would be a pleasure to come again.
Yeah. Thank you then. Okay, let us thank Professor Bhattacharya for nice presentation. Okay. Okay, let us close the session and see you for our next colloquium. Thank you then once and everyone.